seminar. So today is our pleasure to have Professor Tusheng Zhang from University of Manchester, and he will talk about title, reflect the SPDE. Please, thank you.
Yeah, thank you. Yeah, I'd like to thank Alex and also Gertrude for the invitation. It's nice to be back to Queens again. I was here before. Yeah. Today I will introduce you a scheme, a approximation scheme to a class of SPDEs with reflection. Okay, maybe not all of you are familiar with SPDEs, but I will take some time to introduce the equation. But not much finance, but I will mention one application which I learned recently. Okay, from Ben Humbly. I was examining his PhD student. He uses SPDE reflection. Okay. Right. So as I said, we will introduce the approximation scheme for stochastic differential equations with reflection. To establish the convergence of scheme, it turns out I need to study the existence and uniqueness of some deterministic Skorohod-type equation, and also I need to study the convergence of an approximation scheme for the deterministic parabolic problem. Okay. First, let me introduce the equation. So this is the equation. This is a so without this term, so this is the Haidt equation. Okay. So now this is an external random force. So with this we call it stochastic partial differential equation or stochastic Haidt equation. So now we have an extra term which is a random measure which plays the rule of local time, because we are looking for the solution which is non-negative. Okay, that's what we call reflected SPDEs. So just like the ordinary SPDE with reflection, you need some local time. You need some force to prevent the solution from being negative. So I will. This is the space-time white noise. It's a Brownian sheet. Okay, Brownian sheet. So the space variable is the interval 0, 1. This I will write down this equation. So it will disappear. So we have a delicious boundary condition, because this is a boundary 0, 1. So this is a 0 boundary condition. So let me define the solution. Okay. So now a pair, this u and eta is to be the solution of this equation if u is a continuous random field. Okay. So this is a time variable. This is space variable. And it's Ft adapted. Ft the signal field generated by this Brownian sheet. And eta is a random measure. It's not a random field, it's a random measure. Okay? Random measure which satisfies this technical condition and is adapted in the sense that for any deterministic function to C, so this integral is Ft measured. Okay? It's adaptive. It's a very natural assumption. So, and also eta and u satisfy the SPDE in the weak sense of PDE. So which means that if you apply the test function to the equation, to this equation, so this is the inner product in L2, in L2, 0, 1. Okay? So now you use the integration by parts, you move the derivative from u to the test function. So this is simply the weak solution in the sense of PDE. So now this makes sense. So this is the stochastic integral, but with space and time. So this is a random measurement.
Could I ask, Tusheng?
Yeah.
Your 5, 0 equals 5, 1 equals 0.
Yeah.
Fine. Is it that governs the weight x, 1 minus x that you had on the previous slide?
Yes. Yeah. And this condition is also important. So that means the measure only x when u hits the boundary 0. Okay, like local time. So the support of eta is on the set where u is 0 because u is not negative. So if this is 0, so that means eta only x when the u set hits the boundary. So that means you apply the minimum for full. Okay. So this is a definitional solution. Let me see several words about the history of this equation. So it was first studied by Parabolic when the noise is the so-called additive noise, when sigma is 1. Sigma is the diffusion coefficient. And later by Parabolic and his co-author for general sigma, but they proved that there is a minimum solution. They left the uniqueness open there. So several years ago, together with my student, we proved that this is really, the uniqueness also holds actually. So there is a unique solution for this equation, for general sigma. Okay? And later, this SPDE with reflection also can be used to model the evolution of random interface near a hard wall. So this was proved by Funaki and Ola. And later, there are several papers to study the properties, various properties of these SPDEs. For example, Dalam, Müller, and Zampotti, they study the heating probability of this solution. And also by Zampotti, he studied the integration by parts for the law of the solution. I mean, this is a random field. If you think as a path, the two parameter on path space, it is proved that the law has the integration by path formula, also with the sigma constant 1, and also some other properties of study. And also, as I learned recently, Ben Hamblin and Ben and also his student, they proved that the so-called the limit order book. You might know the meaning, but more than I do. The limit order book process actually approximates to approaches to a solution of SPDEs with reflection. Okay, so this is also useful also in finance. Okay, right. So this purpose of this talk is to introduce you a numerical scheme for this reflected SPDE. But there are some, the difficulty is that, first of all, so this is a very singular object, space-time wide noise. So this is not matic, it's not semi-matic. Because of this integral is space and time, so this is a continuous random field, but it's not semi-matic. You don't need formula for this equation. So if you only have a noise in time, then you have its formula also semi-matic. The semi-matic on some L2 space only. But now space-time is very singular. It's only continuous. We only know this continuous random field. And also this is a measure, how to discretize this measure. This is some of the difficulties. Okay. as I said earlier, to prove the convergence of my scheme, I need to study a Skorohod-type deterministic problems, and also I need to introduce a scheme for the deterministic parabolic obstacle problem. This is all for my, but these are all independent interest of this themselves. Okay. Also, I want to mention a few results about the numerical scheme for SPDEs without reflection. So, for example, stochastic equations without reflection, the scheme was introduced by Junger and later by Martina also Sansoulet, and also Junger, and also they studied the numerical scheme for stochastic evolution equation. So these are the results related to this one. Okay, now the coefficient, the assumption on the coefficient are very standard. So this Lipschitz. So Lipschitz both in x. X is a space variable. So this is a unknown variable. U plus Lipschitz and linear groups. So the standard assumption. Okay, what's the scheme? So we only discretize the space variable here. Okay. So how do we get it? So the space variable lives on this interval 0, 1. Okay? So for each n, so we divide this interval into the equal lengths. So this is it. So on this point, I will let the value to be the solution of this n minus 1 dimensional SPDE with reflection. Okay? So this is just notation. Maybe it's a little confusing. This is not value, this is just notation. Okay? You could call this K if you want. So the point is this is a solution for each n. This is a solution of this reflect system of SPDEs, n minus 1 dimensional SPDEs. So this is a local time. This time is really local time. So this is a system reflecting SPDEs, but with dimension n minus 1. So this is a simple notation. It's not a value at this point. Okay? But this system is well defined, it's well studied for SPDE because it's an ordinary system of SPDEs with reflection. Okay? But here, this is a discretization of the Laplacian operator. Okay? So this part actually comes from this discretization of Laplacian operator. And this part comes from this Brownian sheet. Okay? So now let me call definition of the system. So this n minus 1 dimensional solution of the above system is a solution if for each k, so each component is adapted, non-negative, and a continuous process. And eta k for each component is adapted, continuous, increasing process, local time. Okay? And also, of course, this solution satisfies this system for each k. So k is from 1 to n minus 1. Okay? And this is a property satisfied by local time. So the local time on x with the solution hits the boundary 0. Okay? So this is a local time for the kth component of this vector value solution of this SPDE. So this is just the standard definition. So this is non-negative. Okay. So we can rewrite the system in a more compact form, which looks maybe more nicer. So if we call this un fixed n for every fixed n, this is a kth component. So if we call this u and k, so if we define w and k to be this process, then we see that w and k, this is a n-1 dimensional standard Brownian motion, independent Brownian motion. Okay? So if we define for each n, if we define a matrix of n-1 by n-1 matrix, so the element on the diagonals are -2, the neighbor ones is 1, so otherwise 0. Okay? So this is a matrix. So 2, -2, -2, and 1, 1, 1, 1. Okay? So it's n-1. We just rewrite the above system. So then the above system can be written in this nice way. So this is a matrix. So this looks more like the conventional SPDE. Okay? So now I'm ready to introduce my scheme. On this discrete point, I just set my approximating random field to be equal to the value un t k over n. So because it is already a well-defined solution of the system. But in between, I simply use the linear interpolation. Okay, as I said earlier, I only discretize the space variable, not time variable. Okay, so this is a random field, approximating random field. So it's very simple, simple form. But in between, just simply join them by line. Okay. So now the result is the following. So this scheme really convergent. It's really convergent, and for its strong convergence in LP. So before I mentioned the result of Funaki and Euler, they also have a kind of approximation, also with the system of reflecting SPDEs. First of all, sigma is 1, and secondly, they prove that only weak convergence in law, but this is much stronger. Okay. We have more general sigma. So in I think Ban Hamilton and all of his students, they also studied the case when sigma is 1. But as I said, we only discretize the space variable, but now there are no procedures how to discretize the time variable for a system of SPDEs with reflection. So if we combine these two, we can both discretize the time and space. Okay. In this talk, I will only concentrate on the space variable. Okay, now, so next I will tell you how we prove this. Is the main idea how to prove this. So then we need to, first of all, I need to study a deterministic Skorohod-type system. And the problem is because of this structure, it's not easy to directly compare my approximate random field UN with the solution of U. Okay? So the idea is to link this solution to a random parabolic problem, obstacle problem. So then I introduce a scheme for the parabolic obstacle problem. So then I prove the approximating scheme for the parabolic obstacle problem is close to the scheme I introduced. Compare these two. But it's not easy to directly compare this UN I introduced there with the solution of this SPDE because of this random measure. Okay. If you consider differences, how to control. Okay, now, so first let's consider a deterministic Skorohod-type system. So we use, this is the positive part. So given two vectors, we also write as B plus as the, and we take the positive part for every component. So this is the matrix we introduced before. This is the matrix. So it is obvious that this is a negative definite matrix because it's associated with Laplacian operator. But actually this is true, also true. Okay? Now, so this is our deterministic system. We are given n-1 dimensional continuous function, so this will be the barrier of my system. This is completely deterministic, nothing random here. So giving a barrier, so let's consider this system. This is a matrix associated with a discrete Laplacian. Okay? So we consider this discrete, we'll consider this deterministic problem. So we look for a solution of Z which satisfies this ODE and also above this barrier. So here the only data which is given is a barrier. Okay? So we look for a solution.
In your case, your barrier is 0.
Yeah, in that case the barrier is 0. But to prove the convergence, I need this. Yeah, this is just the intermediate step, but it has also its own interest. Yeah, in my case, barrier is 0. But okay, now giving a n-1 dimensional function, let's consider this system. So let me define the solution. So z eta is the solution of the above system. If z is also a continuous function, and z is above this given barrier, here v is given, and eta, each component is increasing continuous function, like a local time, like a kind of local time. And of course, z satisfies this ODE, and this the property of local time in this whole. This means that the eta only acts when the solution hits the boundary. Okay. Okay. Now, the very important a priori estimate is that if we are given two barriers, V1 and V2, then we can bound the difference of the solution in terms of the barrier, the solution of the barrier, difference of the barrier. And most importantly, this constant is independent of n, independent of dimension, because eventually we will let n go to infinity. So the first result is that there is indeed a unique solution to the above system for every given continuous function V. Now, as I said, well, I also need to introduce a discretization scheme for deterministic parabolic obstacle problem. So here we are giving the barrier function is also deterministic. Is a function of two variables t and x. This is x is in our space variable. For given v, let's consider this deterministic parabolic obstacle problem. Okay, we look for the solution of this stochastic parabolic equation with this barrier. We require that the solution is above this real value of the function, this barrier. And this is a measure. Okay. So this kind of deterministic obstacle problem is already discussed in the Mulat and the Bakhtous paper. Okay. Let me recall the definition of solution. Here V is given, the barrier is given. The only given that is barrier, of course, is the initial function. Barrier is given. So we see that this z and eta satisfies the above equation. If z is a continuous function, the solution is a continuous function, and z is above the given barrier, and this is eta is a measure, is a deterministic, is a measure, not random, which satisfies this technical condition, and also z satisfies the equation in the sense of in the weak sense of PDE. Again, we apply test function. Okay, so this also means the measure only acts when the solution hits the barrier. the barrier is minus V, it's not V. Because of my proof of coming to my scheme, I need this parabolic obstacle problem. Okay, now I introduce a scheme, discretization scheme for the deterministic parabolic problem. How do I do that? I will discretize the barrier. Okay. For this given deterministic parabolic obstacle problem, the given data is a barrier. I will discretize the space variable through a discretization scheme for the barrier. Okay? This is a barrier function. I simply define for every n, I define Vn to be this n minus one dimensional continuous function. Okay? So this is the value of this function at this point. So I discretize the barrier, then I can consider the system which I consider in section 1. So this is the deterministic Skorohod problem. For given Vn, I can consider this system. Okay? So now I can define my approximation scheme for this deterministic parabolic problem. I simply join the point by line in linear integration. Okay? So the result, because it is deterministic, so I can prove that this scheme indeed converges to the solution of the deterministic parabolic obstacle problem. So basically I need two steps. First I assume the barrier is nice, smooth, then I approximate the barrier, the general way by smooth functions. Okay, so now I have done the preparations. Let's go back to the proof of our scheme. So there will be many random fields. So you might be lost in that, but the main idea that explain this. We have time. So this is I want to prove UN converges to this, to U. Okay, but it's not easy to directly do this. So what I did is I link this to a random parabolic obstacle problem. So this is called Z bar or U bar. This is a parabolic problem. So now I have, because I already know how to discretize the parabolic problem, I have another, let's see, UN bar. So this is already proved. So what I do is I compare these two. Okay. So I link this, my solution, to a random parabolic obstacle problem with random coefficient. And because my scheme for this parabolic problem, obstacle problem, so then it's enough for me to compare these two. Okay? That's the idea. So then I will introduce many notations. Okay, now let's recall that this is the model form of this solution. So this is the so-called another representation of this solution. Basically, that is the only formula you can use, because as I said, there is no formula. But here, G is the heat kernel associated with this Laplacian equation. Okay. So this is a heat kernel with differential boundary condition. So this is simply the heat kernel. Okay, now. So this is the heat kernel of a Laplacian operator. Now the first thing is we want to write our UN in a form which is similar, which is close to this form. Okay, that's the first thing I want to do. So if I use this UN, remember this is a this UN is an n-1 dimensional solution of a reflecting SPDE. Okay, I can rewrite by the variation of constant formula. I can rewrite my solution using this group generated by this matrix associated with a discrete Laplacian. Okay, this looks more like the form, more like here. Okay. So if I introduce this eta n tx, this is also now the random field, because this is a local time appeared in the discrete system of SPDEs. So now it's already random field. Okay. So if I introduce eta n, this random field, then I can rewrite my approximating solution, approximating random field in this way. Okay. Gn is a kind of a discrete heat current. Okay. So now eta is here. So this will approximate to the random field, random measure eta. Okay. Gn is a kind of discrete heat current. Okay. Now let's compare these two. So let's call this part Vn. So this is this. So this part, let's call it Vn. Okay. The trouble is the random measure. As I said earlier, because of the appearance of the random measure, so it's hard to directly compare this. Then we need to link our solution to a random parabolic problem. Okay, so if I define this random field as V bar, this is a continuous random field, V bar, then if we consider U, my solution U, subtracted by this V bar, then if we call this Z bar will be the solution of the following random parabolic problem. Okay? So now I associate my solution to a solution of random parabolic problem. So the only randomness comes from the barrier. You can solve this parabolic obstacle problem omega by omega. Okay. So now I already introduced a scheme how to discretize this random parabolic problem. So then you can imagine that if you can discretize this system, then you can discretize this Z bar, then we'll try to compare these two. Okay. Now the discretization as before, we discretize the barrier. Okay. So then this is a discretization scheme for the random parabolic obstacle problem. So we already proved this convergence. Okay. So then we know that if we define this as a UN bar, this is a discretization scheme for the random parabolic obstacle problem. So then we know that UN bar converges to U, and to prove the theorem, I just need to compare this UN bar with my UN. To do that, because this is a discrete, so the supremum is simply the maximum of these two difference in these two, and by using the a priori estimate, this is bounded by the barrier. But the problem is this side also contains UN bar and UN. So there are also unknowns. This side also contains UN bar and UN. Somehow we want to use some kind of Gromov inequality if possible. To do that, I need to introduce another intermediate random field. So let's introduce another V head n, which is defined as this. Then, if I consider v head n with Vn, so then we use the Gaussian lemma, so it's possible to control this this means a supernode. So the LP node is bounded by this un bar minus e minus un. So if we start from here, then I introduce this intermediate random field. So what I get is this inequality. So now I can use the Gromov lemma. If I use the Gromov lemma, this will be bounded by this part. Okay, so it remains to prove these two random fields will be closed, which is to 0. So if we write down term by term, so there will be 4 terms. We need to prove that the supraminimum of each of them converges in LP. Okay, this can be done. So we first prove that for each fixed t and x, this will tend to each term will tend to 0 in LP. Then we also try to estimate the two-point motion. So then we can get the convergence uniformly in t and x. Okay. Sorry, there are too many random fields, isn't it? I think I will stop here. Okay. So I was glad to find there are some use in math finance. So give me some comfort to give a talk here. Okay. I stop here.
Thank you.